that are gone. So here is one capacitor. If we were going to put a capacitor here, we have two plates that would have the same length. And this guy is just one battery and one capacitor. So I'm going to label this guy C sub 1. And so when we have, in a simple circuit like this, you know, you could have a switch here if you wanted and shut the switch. Then the current is going, the electric current is going to flow this way. It's going to begin to pile up on this plate of the capacitor. So what you're going to end up having is a positive Q sub 1 pile up on there. I'm labeling it 1 because this is capacitor number 1. And then on the other side of the plate, you're going to have an equal mirror charge, negative Q sub 1, that's going to basically appear there. And so at the end of the day, this should make a little bit of sense to you. I have a positive terminal here, so I should have a positive charge buildup on this plate of the capacitor. I have a negative terminal of the battery here, so I should have a negative sort of charge buildup there. And they're equal and opposite in magnitude just because of the fact that that's the only thing connected there. So when we say a capacitor has charge Q, what we really are saying is that on this plate we have positive Q, and on this plate we have negative Q. So together we say, okay, this capacitor has a charge Q. Now I'm not going to draw it here because it'll get cumbersome, but inside the plates of the capacitor, we really have an electric field. I'll draw it here to the side just to show you. But between the plates we have a little electric field, because electric field always goes from positive charges and they end up and terminate on negative charges. Remember back from earlier in the Physics 3 series. So inside of every capacitor is an electric field. And that electric field, we're going to learn later, is along with the charge that's present, is really what's storing the energy inside of the capacitor, because electric field can store energy. It has the capability to do work. Electric field can move charges around. So when we make this arrangement like this, the larger the plates on this capacitor, the higher the capacitance we have, then the more electric field that we have in there, and the more charge that we have built up there. So we have more energy stored in that capacitor. One more thing I'll say, and we'll keep going in a second. When we have this positive charge pile up here and this electric field kind of spring up here, then what it's basically doing is this electric field is, these positive charges are here and this electric field is here. The negative charges arise, obviously because we're connected to a battery here, but also when you have an electric field pointed that way, then all of the negative charges that would happen to be in this wire right here, they're going to be attracted because the electric field is pointing this way. Remember, in an electric field, the positive charges go with the field lines and the negative charges go against the field lines. So any electrons here in this plate or near this plate are going to be attracted to the plate, the negative charges will, because of this electric field that's in the middle. And also, the positive charges will be on the other side of the plate for the same reason, because the field is going this way. So you can sort of think of these charges on this other plate as induced charges. Charges that, if you want to think about it, the current piles up here, and then this sets up an electric field which then pulls electrons over to the other plate. So they're sort of induced. The reason I'm telling you that isn't because you have to think about that in your circuits. You don't have to think about that in your circuits. But in a second, when I do a proof and show you something, we're going to revisit that in a second. So let's put this on hold here. I think it's fairly self-explanatory. You have positive charges piling up here and negative ones piling up there, and you have some energy storage in that capacitor, and everything's wonderful. So let's go on to adding another leg here. So let's say we have another battery, totally separate circuit. This voltage, I'm going to put this V here. This voltage is also V, so it's the same battery. Could be a 9-volt battery, could be something else. Here's my capacitor, same exact thing as before. I just don't want to clutter up this drawing. So I have C sub 1, and what I'm going to have here is I'm going to go and add another capacitor, and I'm going to add this one. We're going to say this is in parallel. And so when you see two capacitors where they're lined up like this is what's called in parallel. So that's what we're studying in this section. So this could be capacitor C sub 2. And on this capacitor right here, we're saying the same thing as before. This has some Q1 on this plate, and this has some negative Q1 on this plate, and this guy has some Q sub 2, and this has some negative Q sub 2. So it's the same value of the charge, it's just opposite on the other side of the plate. And notice that because these are in parallel, what it really means is they're both connected directly to the battery. That's one thing you have to look at when you're thinking about circuits and just really start to understand it. It only comes with practice. Is you have to think about this a little bit. Pretend this capacitor isn't even here at all. This capacitor really is connected directly to the battery because these are wires that go all the way to the other capacitor. So it's almost like, from this point of view, this capacitor really isn't even here. This guy is connected directly to the voltage source, which is right here. And this capacitor here, yeah, this guy's in the circuit too, but he is also directly connected to the voltage source. So really, you know, it's obvious in this guy. If you were to put a voltmeter, you know, a little meter that you can buy at Radio Shack or someplace else, and if you were connected across there, then you would read, you know, you would read the voltage V. So if this were 9 volts, you would read 9 volts when you connect it across. Because even though the capacitor's here, you're connecting your meter directly to the battery terminal, so that's what you're going to measure. The same thing is actually true here. So if I connect a meter here, you know, and I connect it here, I'm going to measure the same voltage V. So if this is, you know, a 10-volt battery, then I'm going to measure 10 volts. If I put a voltmeter right here and try to measure it. If I put my voltmeter here, I'm still going to measure 10 volts. If I put my voltmeter here, I'm going to measure 10 volts. Because no matter where I am in the circuit, I'm measuring the potential difference between the battery terminals. Now, if there's another capacitor here, or a resistor, or some other electronic component, then that's not true. In other words, you might measure a different voltage. But here, I'm basically connected directly to the battery. So let me draw one more. And I think you get the point, but I really want to make sure nobody's lost. So this will be plus and minus. Let me draw C sub 1 again. And we'll draw C sub 2 again. Right? So the same as that capacitor. And we'll draw a third capacitor, C sub 3. Right? And just to keep everybody happy, I'm going to go ahead and label the same thing. So Q1, negative Q1, Q2, negative Q2, and this will be Q3, negative Q3, right? So there's different charges that are piling up on the different capacitors, depending on the value of the capacitor. And the same thing holds true here. If I take a voltmeter and I hook it up between these two terminals right here, I'm going to measure the same voltage V, because even though all these capacitors are in the way, my voltmeter is really connected directly to the battery. So what I'm trying to say is, and I'll write some of this down in a second, is that when you have capacitors in parallel, every one of those capacitors sees the same voltage as the source that you've connected to, because they're all in parallel. They all see the same voltage. So it's something you need to remember. When you have things in parallel, they all see the same voltage. That's going to be a huge helpful trick for you when you're solving your circuits, to know that when you look at that, it's the same voltage. Because you'll see the equations of circuits aren't that complicated, but you do need to have some intuition to know what's going to happen. That's one of those things I'm trying to teach you here. When you have things in parallel, the voltage is basically the same. Now, when you put them in series, which we're going to look at in a second, that's not true. The voltage is not the same across things that are in series. We'll talk about why here in a little bit. But for here, just sort of memorize that. So the voltage is different. I'm sorry, the voltage is the same. Let me write some of this down. So I'm going to put the voltage is the same across the capacitors. Same voltage. All right, so that's sort of like thing number 1 to remember. Thing number 2 to remember, the charges that are stored in those capacitors are different. Across the various capacitors. You may not realize that at first, but the reason that they're different is because, remember the equation of capacitance, or the equation that relates capacitance. For capacitor number 1, I can say the charge stored on this capacitor is equal to capacitor number 1 times the voltage. Remember, Q is equal to CV. Q is equal to CV. You should remember that. Now, for this guy, let me switch colors here. The charge stored on capacitor number 2 is equal to C sub 2 times V. Notice it's the same V in each case. The voltage is the same because I just told you the voltage is the same no matter what capacitor you're looking at. And then over here for number 3, Q sub 3 is equal to C sub 3 times the voltage. So basically, if you put a 9 volt source here, then there's going to be a 9 volts here, a 9 volts here, and 9 volts here. Okay, but each of these capacitors can be different. This could be, 1 microfarad. This could be 5 microfarads. This could be 10 microfarads. So they're all going to have different values of capacitance. When you do these multiplications, you'll get different amounts of charges stored on those capacitors. So when they're in parallel, the capacitors can have different charges stored on them, which is what I have written down here. The voltage is the same across all of the capacitors when they're in parallel.